So, hello everyone, welcome to BVLSI lecture number 38. So, I am using my old PDF. So, today's date is 2/4/2024. So, we are starting with a different module number 2, which is based on MOS inverters. So, I will be requiring it for few slides and then I will be switching over to the live slide. So, inverter basically is my most fundamental logic gate. What is an inverter? This is the symbol of an inverter. Okay, if you apply A over here as an input, you will get output as A bar. So, it's the most fundamental logic gate which we can implement in VLSI, and of course, we have to implement this in terms of a circuit. Okay, not in terms of the gate symbol. Now, our goal in this MOS inverter is to design and analyze MOS inverters. Okay, the outcome is, what is the outcome of this module? Basic principle employed in the analysis of MOS inverters can be extended to more complex logic circuits like NAND and NOR. So, if you study MOS inverters carefully, we can analyze the same thing in more complex circuits, combinational circuits such as NAND, NOR and beyond. So, MOS inverter design forms the basis of digital circuit design. Alright, VLSI digital circuit design. So, just a saying that inverter is called as a nucleus of digital circuits. It's required. Once the analysis, that is DC and AC, properties of the inverter is well understood, other logic gates such as NAND, NOR, other combinational circuits such as MUX, adders can be understood very well. Okay. So, with this, let us start with the analysis of MOS inverter. So, let's start writing. So, again, this is the live PDF, lecture number 38. So, this is my inverter symbol. I am just drawing the inverter symbol over here. This is A, Y equal to A bar, and this is my inverter symbol. Alright, what's the truth table for this? If A is my input, Y is equal to A bar is my output. If A is 0, Y should be 1, and if A is 1, Y should be 0. Okay, so this is my truth table. Very simple so far. And if I plot a graph of, listen carefully, this is important. So if I plot a graph of V out versus V in, how the graph should look like? What do you think? Yes, the graph will look like this. Oh, it will touch almost 0. It will be a line parallel to the x-axis. Here, this is VDD. This should be ideally VDD by 2. Alright. So, what do we interpret it from here? This is VDD. This is 0. This curve is called as voltage transfer characteristics of ideal inverter. V out versus V in is called as voltage transfer characteristics of ideal inverter. Alright. The threshold voltage for this inverter is at VDD by 2 for this ideal inverter. So, this is the threshold voltage of inverter. Okay, VTH. VTH for the inverter is VDD by 2 ideally. This is called as voltage transfer curve. Now, let us decode this curve. Let us understand what does it mean. Now, if you see carefully, I am plotting V in on the x-axis, pay attention. So, when V in is very low, let's say V in is between 0 and less than VDD by 2, what should be my output? V in is low, right? So, what should be my output? So let's take some numbers. Let's say VDD is 5 volt. Okay, this will be how much then? 2.5, and this will be 5. So what I am saying is between 0 to less than 2.5, my input is low, so what should be my output? High. So this is my logic 1 output. Is it not? So my output is at VDD over here. And if I increase my input beyond 2.5, that is beyond 2.5, then I can say that my input is increasing to a higher value. So what should happen to the output now? Output should fall to a low value. So this is called as logic 0 output. Got it? So as an observation, what we can do is, what we observe over here is, please draw the diagram. So all the inverters should follow this curve. All the MOSFET inverters. VTC curve will tell you about how well we define logic 1 and logic 0, whether it's input or at the output. So for any input, we can write in statement form, for any input between 0 and VTH, that is 0, Vin is greater than 0, less than VTH, what should be the output? Output is equal to VDD, right? Which is termed as logic 1. Yes or no? Then, what else happens? Output switches from VDD to 0. When does it switch VDD to 0? When we can say Vin is equal to VTH. Yes or no? Whenever Vin is equal to 2.5, output switches from VDD to 0 drastically. Ideally, that is true. So automatically when the input reaches 2.5 volt equal to 2.5 volt, your output will switch from VDD to 0 instantly. This is what should happen. Alright. Third observation is, for any input between VTH and VDD, that means Vin is less than VTH and Vin is greater than VDD, greater than VTH and less than VDD, what should happen at the output? For any input falling between VTH and VDD, what should happen? Output voltage is equal to 0 volt, okay, which is interpreted as logic 0. Yes or no? Yeah? Is it clear from the curve? Now we'll write 2 more points. So we can say now that an input voltage between, we can write this, an input voltage which has this level between 0 to VDD is interpreted as logic 0. Correct? This is logic 0 input. Any input between 0 to VDD is interpreted as logic 0. Similarly, we can write an input voltage between VTH and VDD is interpreted as logic 1. And from the VTC curve, it's very evident that the transition between logic 1 and logic 0 occurs abruptly at an input voltage Vin equal to VTH or VDD by 2. Okay, where VTH is called as, write down, VTH is called as threshold voltage We have threshold voltage for the device, but this is different. This is threshold voltage of inverter. Alright, or it is also called as transition voltage of inverter. So far we have understood there is a VTC curve for an ideal inverter, and all these observations are the interpretations from the curve written. Yeah, this is how a basic inverter should have the characteristics and its observation. So there are 4 levels: input logic 0, input logic 1, output logic 1, output logic 0. Yes or no? Ideally, these are ideal all. Now let's go to further. We'll draw the general structure of NMOS inverter. So write down next. General NMOS inverter. Okay. So general NMOS inverter looks like this. We have enhancement type MOSFET. So enhancement type MOSFET will have a dotted symbol over here, indicating that the channel is not formed yet. 4 terminal symbol we are using, and as a load we are drawing a dummy box. It can be any other thing. This is VDD. It can be a resistive load, it can be some other terminal, some other device. Okay, this is now identify the terminals for me. Acha, tell me, what is this terminal? This is gate, this drain, this is source, and this is substrate or body. So it's a 4 terminal MOSFET. And where do we apply the input? Here, between the gate and the source terminal. Okay, so all the voltages are measured with respect to source being grounded. Where is my output? I should have an output also now. So output is measured across drain terminal. Drain terminal. Okay. The voltage across the load, we can call it as VL, and the current will be flowing through this device. This is basically how many terminal device we can connect over here. If we connect a load, how many terminal it should have? There are 2 terminals, above and below. So it should be a 2 terminal circuit element. This load should be a 2 terminal circuit element. It can be a resistor or it can be an active load itself. Okay. So why it is called as an NMOS inverter? Because this device over here, which I have shown, this is called as NMOS driver. This is called as NMOS driver. And what do we connect over here is called as load. It can be a resistive load, enhancement load, depletion load, or PMOS load. Okay, so few observations we can write over here. From the circuit diagram. Okay, can you all tell me what is V from the circuit in terms of terminal voltages of the MOSFET? V in is equal to VGS. Yeah, correct. What about V out? It's VDS. What about substrate bias voltage, meaning VSB? Source and body voltage are at 0, right? So the threshold voltage which will use is VTO without the substrate bias effect. Okay. So under DC conditions, no current flows in and out of the input or output terminals of the inverter. Okay. Now, depending upon the type of load, depending upon the type of load, we have 4 different types of loads over here. Depending upon the type of load, 4 different types of inverters. So here we write the heading types of NMOS inverters. Number 1, resistive load. Resistive load NMOS inverter. Second is enhancement load. Enhancement load NMOS inverter. Next is depletion load. NMOS inverter. And the fourth is the most famous PMOS load NMOS inverter, which is also called as CMOS inverter. So for y'all in your syllabus, y'all have the detailed analysis of resistive load NMOS inverter and CMOS inverter. Whereas other two we have to study in comparison form, comparison to other inverters. Okay? So we have in your syllabus resistive load NMOS inverter, its analysis, numerical design. CMOS inverter, analysis, numerical design. And rest of the inverters you have to study in the comparison basis. But the characteristics of the inverter circuit will actually depend upon, very strongly upon, the type and the characteristics of the load device. Okay? So it depends upon whether it's a resistive load, enhancement load, depletion load or PMOS load inverter. Now, completed this? Alright. Now we'll draw the actual or a practical VTC curve. Ideal VTC curve is how? How do we draw ideal VTC curve? Alright. This is what we have seen, right? This is VDD, this should be VDD by 2. This is my V out. This is my V in. This is ideal VTC. Practically, if you connect, very soon we will be seeing this. Practically, if you want to see this curve, how it will look like? It will look like this. The transition from logic 1 to logic 0 is not sharp, it's smooth. Okay? And this transition also may not go to 0 instantly. It will take some time. So this is a practical VTC curve. Okay? So this is the VTC curve for a realistic NMOS inverter. Let me not write this VDD by 2, these are ideal values. Now here I will define certain things, so pay attention. Are we ready? So this we are drawing it for generalized NMOS inverter. So this is my generalized NMOS inverter, which I am drawing again for your reference. This is my load. I don't know what should be my load. VD. That's my V out. That's my V in. So this is my NMOS inverter, generalized form, where the load can be any of the 4 types. Now listen here. Here, this maximum value which is attained by this curve is called as VOH. The minimum value attained by this curve, output curve, is called as VOL. So let's say this VOL almost, it's not always equal to 0. It might be some value over here. So this is may or may not be equal to 0. This is VOL. Ideally we want it to be equal to 0. Now see, how do we measure VIL? So the first time this curve goes down, let me show it to you. You take a tangent of that. Okay? And that tangent, you extend it down. This point is called as VIL, input low. And the last time this curves, flattens out, you take a tangent again, and that tangent you extended here, this is called as VIH. So what is happening when we take a tangent? That means we are taking dV out by dV is equal to -1, right? Here also the slope is equal to -1 at these 2 points. And lastly, when we plot the graph of V in equal to V out, see, this is V in equal to V out curve, right? A straight line. This, if you extend it down, what you should get? VTH, threshold voltage of the CMOS inverter. That is what you should get. Alright. So what are the 4 critical parameters here we have? VOH, VOL, VIL, VIH and VTH. So these are the 4 critical voltages which we need to find out for all the inverters. The expressions we need to find out, because they will decide the noise margin levels of the inverter. Okay? So shall we analyze this curve now? We'll analyze this curve, we'll write observations. Alright. Can we start? Important observations. What is this curve called as? Practical VTC curve for a realistic NMOS inverter. I hope you have completed up till here. Our aim is to find this expression of these 5 critical voltages: VOH, VOL, VIL and VIH and VTH. Now, the important observation number 1 is, for very low input voltages, that means my input is very low. What should be my output? It's an inverter. For very low input voltages, for this values, V in is very, very low. What is my output? High. VOH. We call that output high. VOH is called as VO means output and H means high. So, for very low values, for low input levels, my output is at almost equal to VOH. This VOH itself can be VDD. That is a different story, but we call it as a VOH. Okay? Can we say, if this happens, output is equal to VDD almost, can I say my driver NMOS is off in this case? Because my input is low, na? Not enough to turn on the device. So I can say over here, my NMOS driver is off. So if this NMOS driver off, what will be my current will be? What will be my current through the diode? The current through this NMOS. ID will be 0. Yes? So IL will be equal to 0. If there is no voltage drop across the load, my VDD will be equal, Vout will be equal to VDD. That is what it is, right? So I can say over here, therefore my Vout will be equal to VOH. That is what we have written earlier actually. Okay? Now, second observation is, as my input Vin increases, what is happening? As my input Vin increases, my Vin becomes greater than VTO, threshold voltage of the inverter. And what is Vin? VGS. So VGS greater than VTO means what? NMOS starts conducting. So NMOS turns on. When the NMOS turns on, what happens to current flow? ID starts flowing. And whenever ID starts flowing, there will be IL also. So what will happen due to that? Some voltage will be dropped across the load also. So that means what will happen is, as Vin increases, my VR starts to decrease. Yes or no? So from the curve, as you go on increasing your Vin further, my Vout value now will start to decrease. The drop in the Vout is gradual and has a finite slope. Okay, so if you see carefully, the general shape of this VTC curve is different from the ideal curve. Ideally, the switch between logic 1 and logic 0 was very sharp. Here it is smooth. This is the transition from logic 1 to logic 0. This is very, very smooth. Okay, now we have identified two critical parameters on this curve where the slope of this VTC curve becomes -1. Now what is -1? This is slope equal to 1, na? Arey, V in equal to V out, slope is 1, na, here. What is opposite of that? 90 degree line. बराबर ना? ये 90 degree line बनाओगे तो इसका slope कितना होगा? -1. That is what the lines we are making over here. Okay? So perpendicular to this lines will have a slope of -1. We take two critical points, one over here and one over here, when it was about to fall down and here is about to become flat. Okay, so here whenever slope of VTC curve, what is slope of VTC curve? dV out by dV becomes equal to -1, the smaller input voltage which satisfy this equation number 1. The smaller input voltage which satisfy this equation number 1 is called as VIL, which is called as input low voltage. The smaller of the two input voltages which follow this is called as VIL, and the larger input value which satisfy dV out by dV equal to -1. It will be only at one point only, right? At one point only the slope will become -1. So there are 2 points it happens over here. Okay, so the larger input value satisfying this equation number 1 is called as input high voltage. So from the slope we get two values, VIL and VIH. Agree? So this VIL and VIH will help determining us the noise margins of the CMOS inverter or of any inverter circuit. Okay. Now let us go further in this. Next is, as you go on increasing the value of V in now further, let's say it is beyond VTH now. So V in increases further, matlab beyond VTH also now. So what will happen now? The output will continue to drop. The output continues to drop, and finally it will continue to drop and it will reach a value of VOL. Now VOL may be 0, may not be 0, and reaches output low voltage. VOL is called as output low voltage. What was VOH called as? Output high voltage, and VOL is called as output low voltage. So when this is happening, whenever V in is greater than VTH and increasing further, if you see carefully, the output will continue to drop down until it reaches settle down at VOL value. Now this VOL ideally should be 0, but practically for other inverters it may not be equal to 0. So that's why we define it as output low. Alright. Now let's define these 5 critical parameters together in statement form. So write down. Completed up till here? Observations from this practical VTC curve. Now let's write down the typical definitions of this 5 critical voltages. On the VTC curve. Okay, that characterize the input output behavior of the inverter circuit. So first is VOH. How do we define this? Maximum, it is the maximum output voltage when the output level is logic 1. The maximum output voltage when the output level is logic 1. VOL minimum, it is the minimum output voltage when the output level is logic 0. Alright? We will discuss why it is minimum and maximum later. Okay? Why not this is called as maximum, why not this is called as minimum, we'll discuss later. Next is VIL. Anyone? Maximum input voltage which can be interpreted as logic 0. Maximum input voltage which can be interpreted as logic 0. Next is VIH. Minimum input voltage which can be interpreted as logic 1. Alright, these are the 4 critical parameters. Now 5th one, VTH, the point on the VTC curve at which V in is equal to V out is called as threshold voltage or inverter threshold voltage. This is called as inverter threshold voltage. So for all the inverters, we have to find this 5 critical parameters, all of them. In fact, we are doing the analysis in detail for 2 of them, resistive load and CMOS. So we have to derive them also. We have to solve numericals which will calculate these also. Are you understanding? All 5 of them. We have derivation for resistive load, CMOS inverter. Enhancement and depletion, you don't have derivations, you have comparison basis only. Like we have done in experiment number 2 in BVLSI. Okay? These definitions will imply that logic levels in digital circuits are not quantized voltage levels, but are represented by voltage ranges. What do we know previously in digital logic? That logic 1, it's a range. It's a value, right? When we say logic 1, what do you understand by it? We have understood previously it's 1, it is VDD, and logic 0, 0. This interpretation has to change. Now we are saying logic 1 is a range, logic 0 is a range, and that is well explained by these 5 critical parameters, actually 4 of them. So write down the definition of noise margins actually. So write down the ability of an inverter to correctly interpret an input signal within a voltage range as either a logic 0 or as logic 1. Is important. This will allow the digital circuit to operate within a certain tolerance to the external signal disturbances. So let's say the input due to disturbances might change, right? So if you are within the safe range of the input, we are immune to it. Okay, so we are immune to the external noise. The tolerance will vary depending upon the external factors, that is for sure. So unwanted signals can couple through the various parts of the inverter, and it can treat that input which is logic 1. Let's say we have defined input, these are levels, right? So let's say input logic level high is input level high, which is correctly interpreted as logic 1. Okay, this level is from 5 volt to 3 volt. Okay, and logic 0, that is input side only. What input can be correctly interpreted? So let's say it's 2 volts to 0 volt. So this is input level low. Okay, so these are levels: input level high, input level low. Now if a noise comes into picture, okay, when it will disturb the system, when it falls out of this range, when a noise is disturbing, let's say it's at 2.8 volt, then definitely our circuit is vulnerable to the external noise. But if it falls in this range, then a system remains immune to the external noise. Are you understanding? Yeah. This is an example I've given you. We will take an example now next to understand how the signal propagates to the inverter. So that example will explain you what will be the minimum. You know, in the definitions we have written over there, maximum output voltage, minimum output voltage, maximum input voltage. Why we have written, now we'll explain that with an example. Can we start? I want to take a ready-made example. Okay, so I'll use the other PDF. So all these in details are there over here, so you can read about it. We have written the main points. If you want to refer to the details, you can refer in this PDF. Now write down this topic heading: propagation of digital signal under influence of noise. So how will my noise affect my circuit reliability? We'll understand that. Okay. Don't draw anything, just write a heading, that's it. Later on, if you have understood, then you can draw. Okay, everyone, concentrate over here. I have 3 inverters. All the 3 inverters are identical. This is inverter number 1, inverter number 2, inverter number 3. They are identical inverters, all have same characteristics. Input voltage of inverter 1 is VOH. This is an assumption. Output voltage of inverter 2 is VOL. These are the assumptions. All the inverters are symmetric, and input voltage of inverter 1 is logic 1, and output voltage of inverter 1 is logic 0. This is VOL. Agree? So far so good. So the output signal at the output of inverter 1 is being transmitted to input of inverter 2 via interconnect. See, in VLSI, when we connect any device element to other, we don't say wire, we say interconnect. Okay, so the wire in discrete world, in integrated circuit world, we call it as interconnect. Interconnect means wire only, it's made up of metal or polysilicon. Alright, so the noise can enter via these wires. Yes or no? So let's say it will enter this wire. So what will happen now? So on-chip interconnects generally are prone to signal noise. See, in the wires, the interconnects can pick up noise signals. If there is an analog signal and there is a digital signal parallelly moving around, the digital signal is constantly changing, so analog signal can pick up that noise signal. So that is what is called as cross coupling. Anyways, so this interconnect over here is prone to external noise. So noise can affect this interconnect, the signal transmitted via this interconnect. So this logic 0 is transmitted to the input of inverter to, yes or no? So let's say it is prone to the noise. So let's say this signal which was logic 0 has been disturbed due to this noise. So what will happen now? The voltage level over here let me show it to you. The voltage level over here, which is called as input voltage low, बराबर है ना, VIL, we call it as a VIL, maximum allowable voltage. Why we call it as a maximum allowable voltage now, tell me? Why it's not minimum? Or the maximum input voltage it can take. Okay? Yes. Since this is VOL, this has to be VIL. बराबर ना, input side है, and this is maximum allowable voltage. So what is the maximum allowable voltage? It can correctly interpret it as logic 0. बराबर ना? Right? So the consequence will be that the voltage level at the input of logic of the inverter 2 will either be larger or smaller than VOL. बराबर है ना? ये जो voltage है, this VIL can have two cases. It can be greater than VOL or it can be less than VOL. Which is we want? What do we want? If the input signal of the inverter 2 is smaller than VOL, is it good or bad? Is the signal correctly interpreted as logic 0 by inverter 2? Yes. अरे input कम है ना, is low, right? So this means VIL less than VOL means my input is correctly interpreted as logic 0 at the input of inverter 2. Correct? अरे logic level 0 है ना, input low. So if VIL is less than VOL, let's say for that matter, then my input of the inverter 2 is correctly interpreted as logic 0. ये logic 0 ही है ना input. So it's correctly interpreted in this case. Okay. Now let's say if input VIL becomes greater than VOL, what will happen? Input voltage actually wrong लिखा है. If input voltage of this inverter becomes greater than VIL of the inverter, then what will happen? Due to this noise signal will give it to you, V in will be VIL plus noise signal, right? So definitely input signal can be greater than VIL. So what will happen now? Tell me. So when input signal becomes greater than VIL of this inverter, ये VIL fix है ना, इसका range है ना. Let's say the VIL range is from 0 to 1 volt. And because of noise, मेरा input becomes greater than 1 volt. Then वो correctly logic 0 interpret कर पाएगा? No. So between 0 to 1 only it can do. So what is the upper limit over here? 1 volt. So that's why it's called as maximum allowable voltage. So 0 to 1 तक ये correctly interpreted करेगा logic 0. Or else it will interpret it logic 1 or something else. So what is the condition on this? That if input voltage is greater than VIL of the inverter, then it cannot be correctly interpreted as logic 0. Okay, so that's why it is called as VIL is called as maximum allowable voltage at the input of inverter number 2, which is low enough to ensure logic 1 output. Here यहाँ पे ये वाला. Okay, इधर तक समझ गया? Any problem in understanding this? Now consider the transition. अभी ये input low हो गया ना, ये let's assume it's correctly interpreted as low, logic input low. So what it should produce at the output? VOH. Yes or no? Input low होने की वजह से let's say is correctly interpreted as logic 0. Now we are applying logic 0 now correctly to the input of inverter number 2. So inverter number 2 का output क्या होना चाहिए? VOH. Are correct ना? Now what will happen? Let's see the transition between inverter number 2 and 3. Now, this again, can be a noise interference connecting the interconnect also. Yes or no? Now, let's say, what is this? If this is VOH of inverter number 2, what is this? This is VIH of inverter number 3, correct? Minimum allowable. Now we'll understand why it is called as a minimum allowable voltage. Barabar na? So, this VOH should be such that when transmitted via the interconnect, it should be correctly interpreted as logic 1. Let's say the range of this input is 5 volt to 4 volt. बराबर है? ये इसका अपर रेंज है. So VOH is 5 volt, no problem. VOH is 4.5, it will still correctly interpret it. If VOL is 4 volt, still correctly interpret it. Logic 1 तक बराबर हो रहा है. अभी whenever V out, इसका V in actually we can say V in of inverter number 3, as long as it is greater than VIH, no problem, right? Now if water V in is less than VIH, so this is acceptable. What will happen if V in becomes less than VIH? मतलब ये क्या बोल रहा है? VIH has fallen down below 4 volt, then it cannot be interpreted as logic 1 input. बराबर समझ रहा है? So ये मिनिमम लेवल है, ये मिनिमम लेवल है ना, यहाँ पे 5 to 4 मिनिमम लेवल है, राइट? 4 के नीचे ये क्या था? ये मैक्सिमम लेवल था, ये मिनिमम लेवल है. दैट्स व्हाई इज कॉल्ड एज मिनिमम अलाउएबल वोल्टेज. समझ में आ रहा है? सो VIH इज कॉल्ड एज मिनिमम अलाउएबल इनपुट वोल्टेज, which can be interpreted as correct logic number 1. Did you understand? If the noise affect the system, your V should be less than it should be greater than VIH to correctly interpret it as logic number 1. Then only this can take, अगर ये logic number 1 हुआ, then only it can give VOL, right? Or else wrong हो जाएगा. Yes or no? Now let's consider this case that there is something wrong. Let's consider this case only. This VOH somehow it was, let's say, 4.5 volt. Due to noise it has become 3.5 volt. तो ये wrongly interpreted क्या करेगा? It will cannot interpret logic 1, so it will wrongly interpret logic 0. So output में क्या आएगा? Logic 1, which is wrong. Correct? It should interpret it as logic 0, right? VOL आना चाहिए तो VOH आ गया. So this is what will happen. So what is to be followed over here? These noise margin levels, these values or ranges should be higher. Okay? So this is the effect of the noise on the circuit reliability or propagation of digital signal under the influence of noise. Yeah. Now your doubt is clear? So that's what happening ना here. देखो यहाँ पे यही तो gap है. Output has become 3.5, which is the input to this. So it's wrongly interpreted. Inverter number 3 will wrongly interpret it as logic number 0. Logic 0. Logic 1 होना चाहिए था, but it's treating it as logic 0. So wrong हो गया ना output. So that is what happens. That's why you should ensure that VIH is the minimum allowable level at the input of logic, the input of inverter number 3, which is high enough to ensure that a logic 0 output. Okay, with this aspect will define noise margin levels. So let's do that, the last part of today's lecture. समझ में आया? So write down noise margin levels. So these are actually, we call it as noise tolerance for digital circuits. So noise immunity of the circuit will increase with noise margin, correct na? So noise immunity, immune to noise, increases with increase in noise margin. Then there are two types of noise margins. Two noise margin levels. One is NML, which is noise margin low. So this is noise margin for low signal levels. Correct? Noise margin high, this noise margin for high signal levels. Now the next diagram which I am drawing is extremely important. Do it. Draw it please. Draw two levels. On one side we draw V in, on the other side will draw V out. If one understands this, then your job will be over. This level this range, this side we call it as VOH, and this range we call it as logic 1 output. Okay, and this range over here on this side, this is input side now, there is a range here also. Okay, this side we call it as VIH, and this range is called as logic 1 input, correct? Next, let's extend this slightly down. Now there is 2 more ranges there left. This range over here, of course this and this coincide, ये levels. अपर लिमिट क्या है इसका, समझ रहे हैं अभी? मैक्सिमम अलाउएबल वोल्टेज, मिनिमम अलाउएबल इनपुट वोल्टेज. दिस रेंज इज कॉल्ड एज logic 0 input, and one last is there. Can anyone guess? VOL. This range, logic 0 output. You know what are noise margin levels over here? ये देखो, extend this over here. This is noise margin high. This is noise margin low. And ये in between क्या है? ये क्या है? Uncertain region. Correct, na? These are graphical representation of noise margin. Okay? What if you may say VOH is equal to VDD? Yeah, fine. Its limit up till here only. VOH, yes, it can be. If VOL is equal to 0, yes, it will stop over here. Yes or no? So, as you rightly said, output levels are very, very small. Logic levels, range है ना, ये range है ना. Logic 1 output high, logic 0 output, logic 1 input का range ज़्यादा है. Noise can enter the input signal, that is bigger, the green portion, yeah, definitely. तो हाँ, अभी यही same example, समझा? तो थोड़ा सा भी voltage will disturb the output. Yes or no? That's why we have to be careful with the input ranges. We have to be careful with the output also, definitely yes. So we have to design a system which will have a large noise margins. But the noise margin high, noise margin low should be large enough so that this uncertain region is quite small. समझ में आया? This is the aim of any inverter. So from here, can you define graphically what is noise margin high, noise margin low? Can you write noise margin high? Formula? So it is VOH minus VIH, and noise margin low is VIL minus VOL. That's why we find these 4 critical parameters first from the VTC curve, and then we say we have found out the noise margin levels. So in this graph, the shaded portion will represent the valid high and low voltage levels for input and output signal. Again I repeat, the shaded portion, the highlighted portion over here represents the valid high and low voltage levels for the input and output signals. Okay? Yes, what is the uncertain region we are talking about? The voltage between VIL and VIH is the uncertain regions. That cannot be correctly processed as either logic 0 input or logic 1 input by the inverter. समझ रहे तुम लोग को? So reducing the width of the uncertain region is probably the gain of probably the goal of a CMOS inverter or any inverter for that matter. The higher the noise margin, the better is the system. Okay? Fine. I guess that's it for today. So today we are ending the lecture over here, and tomorrow we'll start with NMOS resistive load, NMOS inverter. Alright? You have any doubts? So from now on we will be deriving this noise margin levels for every inverter which we encounter for. So that's it for today.